So we've looked at limits numerically and algebraically, and today we're going to look at what happens when x approaches infinity, positive or negative infinity, as opposed to approaching a specific number. And we have a function here. It's a basic reciprocal function. So f of x is equal to 1 over x. And what we want to look at is what happens when x approaches positive infinity to that function. And as you look, as x increases, my y value looks like it's approaching 0. So what we can say is as x approaches infinity, f of x is approaching 0. So the limit as x approaches infinity is going to be 0. And that's the same thing for when x approaches negative infinity. If you look at your graph, as x is increasing in the negative direction, my y value, if I followed along, it's approaching 0. So think about why that is. We've talked about this in class. When x is 10, well, f of 10, I need my pen, f of 10 is 1/10. f of 100 is 1 over 100. f of 1,000 is 1 over 1,000, and it keeps going. So the greater the x value, the greater the denominator. And the greater the denominator, the smaller the overall number is. So that's why that happens. So we can define a rule for the limit of a specific function as x approaches infinity. And here it is, the limit as x approaches either positive or negative infinity, doesn't matter which one, of the function 1 over x, that limit is going to equal 0. And we're going to work with that concept throughout the next few examples. Now the same thing applies if I have that value raised to an exponent. So the limit as x approaches positive or negative infinity of 1 over x to the n, that also approaches 0. In fact, it approaches 0 faster than the original one. So we're going to use this concept to evaluate some limits at an infinity. So here's an example we're going to look at. We're going to evaluate as x approaches positive infinity this function, 5x squared minus 2 over x squared plus 1. It's a rational function. It has areas of discontinuity. And here's what we're going to do. The process is this. We're going to divide every term by the highest degree term in the entire function. So the actual value of the function is not going to change. We're just kind of rearranging the terms a little bit by the highest degree term. So when I look at my function, my highest degree term is an x squared. So I'm going to divide each term by x squared. It's equivalent to multiplying every single term by 1 over x squared. So when I do that, I end up with the limit as x approaches infinity of 5x squared over x squared minus 2 over x squared, and then all over x squared over x squared plus 1 over x squared. And then what you do is you can evaluate each limit. Evaluate the limit of each term. So, knowing that the limit as x approaches infinity of 1 over x is equal to 0, or 1 over x to the n is equal to 0, I can look at all of these terms. And when I do that, this guy would approach 0. This guy would approach 0. This one simplifies to 1, and this one simplifies to 5. So when I am done, I end up with 5 over 1. So that has a limit of 5. when I look at it. All right, we're going to look at the graph of the function that we just evaluated, my rational function. And remember, we had a limit of 5. If we look at this graph, and I know not all of the markers are showing up here, but they do show up on your paper. And let's look at the horizontal asymptote. When you do that, you'll see that the horizontal asymptote is, in fact, at 5. And how we've defined horizontal asymptotes in the past is the fact that they are what is happening to the graph as x approaches positive and negative infinity, which is the same thing as evaluating the limit at x as x approaches positive or negative infinity. So the limit of this function is in fact the horizontal asymptote. It's defined here. The line y equals L is called a horizontal asymptote of the curve if the limit of f of x as x approaches infinity is equal to a certain value L, or as x approaches negative infinity. That's how we can find the horizontal asymptote, by evaluating the limit as x approaches positive or negative infinity. Now, another way to evaluate the limit, instead of dividing each term by the highest degree, is to look at 3 cases, and we've done this before. We've done this when we looked at the horizontal asymptote of rational functions. So it's the same process, because we've just equated the limits to those. Limits at positive and negative infinity of a rational function can be evaluated by considering the ratio of the highest degree term in the numerator and the denominator. The highest degree term in standard form, you would have the highest exponent. So you're going to look at the coefficients after you look at the highest degree terms. And there are 3 cases. If the exponent of the numerator is less than the exponent of the denominator, then what you basically have is, when at large values, you have the function 1 over x, which we've just figured out that the limit of that is going to be 0. So if this is the case, then the limit as x approaches positive or negative infinity of that function is equal to 0. Just like we used to say, when the denominator has the higher degree, the horizontal asymptote is 0. This is the same thing. So when we have, in the second case, when we have the exponents the same, so they are the same degree. We've talked about this before. When everything is the same degree for large values of x, everything divides away except the ratio of the coefficients. So when this happens, the limit as x approaches positive or negative infinity of my function, that's going to be equal to the ratio of the coefficients of the leading terms. And then, in the third case, if my numerator degree is greater than my denominator, there's no limit, because the function just keeps increasing. So in that case, we say the limit as x approaches positive or negative infinity of f of x does not exist. The limit does not exist. So we will finish by talking about a couple of examples. Here's the first one. X is approaching infinity. I have 4x over x squared plus 7. Instead of dividing every term by the highest degree term, we're just going to look at the ratio of leading terms. So the degree of the numerator is first. The degree of the denominator is second. First degree over second degree. That means the denominator is bigger, and the limit of that function is going to be 0. For the second one, the degree of the numerator and the denominator are the same, so it's the ratio of the coefficients. So that guy, the limit's going to end up being 3 over 2. Now remember, this only works when x is approaching positive or negative infinity. We have the whole other set of rules when x approaches a specific number.